Week 11, part 2. Okay, so here are Maxwell's equations in empty space, and we note the wonderful symmetry between electric and magnetic fields in here. And now I want to take you through Maxwell's discovery. We're going to do this in a much more simplified way than what Maxwell did. In general, these equations apply to all types of electric and magnetic fields. And electric and magnetic fields are vectors, meaning they have x, y, and z components, but those components are themselves also functions of position of x, y, z, and also of time. So it's a pretty complicated beast, the electric field and the magnetic field, and those equations can get rather involved to try to deal with all of that variation. We're going to look at a very simplified version of this. We're going to say that the electric field only has a y component, and it only varies in the x direction. As you move along the x-axis, this y electric field varies. And it might also vary with time. In the same fashion, we'll say that the magnetic field has only a z component, but varies also along the x-axis and time. So with those beginnings, let's take a look. This is going to get a little bit involved. Just try and follow as much as you can and don't worry about the parts you don't follow. So if we look again at this simple case where we've got a y electric field and a z B field. Here is a picture of the x, y, and z coordinates, and here is the y component of the electric field, and here is the y component of the electric field at a different x position, and that's why the arrow is a little larger. So apparently the electric field is growing as you move down the x-axis, or it could be. The magnetic field, meanwhile, is pointing off perpendicularly in the z direction. It could also vary as we move along x. I haven't tried to draw that. We're going to consider walking around a little path here, this little path that has a delta y and a delta x that later on are going to become infinitesimal, but for now we'll draw them as big changes in y and in x. So we walk around this path, and we're going to use Faraday's law as we walk around that loop. Faraday's law says that the electric field dotted with the little elements of our path should equal the rate of change of the B field over that area. Okay, so let's look at the pieces on the left, walking around that path. Well, the path has 4 steps. Let's start on the right, and we move up using this y component of the field. That's what we would get when we took the dot product with our y path. So we'll have the y component of the field times whatever our y displacement is. That's what we would get during that little part of the path. The y field times the y path, and it's the y field at x2. That's the value right there. Then as we go across the top, we wouldn't get anything, and that's because the field is pointing up. Remember, the field only has a y component, but our path is moving in the x direction, and so the dot product of those two will give us 0. When we come down on the left-hand side, then it's the y component of the field times delta y again, but it's the y component at x1, and there's a minus sign because we're moving down, but the field is pointing up, so the dot product brings in a minus sign. And then finally, moving along the bottom, we'll get 0 again because the electric field is pointing straight up and our path is pointing straight to the right. So they're perpendicular to each other, and the dot product gives us 0. All of that is supposed to equal the time rate of change of the B field flux through this surface here. And so I'm just going to call that the z component of the field times the area of that surface. I'm going to ignore any change in the B field across this surface and just say, it's uniform enough, especially if we make the x and y changes small. We can ignore that. And so it's just d by dt of bz, the z component of the field, times the area. Okay, now let's do some simplifying. So if you look up here, first, all I do is gather together the terms that have a delta y in them. And so it's ey at x2 minus ey at x1 times delta y. And over here, I just copied the same thing. Now, if you remember a little bit of calculus, you can say that the change in some quantity from x2 to x1 can be expressed as the rate of change times the difference between x2 and x1. How steep is the function of the electric field? How quickly is it changing times how far did we go? That will give us the difference between the two values. So that's how I've written that. Then multiplying by delta y. Then over on this side, that area, what's going to be the area of this surface up here? Well, ultimately, that's just delta x times delta y. So I put it in right there. So now if you look at this, you see, well, shoot, we've got delta x times delta y on both sides. We can just cancel those out and have a much simpler expression. And what it says here is that the rate of change, well, the change of the electric field with respect to x is related to the rate of change with time of the B field. Now, I'm not going to go through the math, but if instead of starting with Faraday's law, we had started with Ampere's law, we could get a similar expression. We could do the same kind of thing, and that's down here. You start with Ampere's law, and using steps that I haven't shown at all, you end up with this expression, which is kind of comparable to what we have there. It's just sort of the other way around. Now you're taking the derivative with respect to x of the magnetic field. Over here, it was the derivative with respect to x of the electric field. And that's related to the time rate of change of the electric field, just as this was the time rate of change of the magnetic field. Still a lot of symmetry here. These electric and magnetic fields are acting kind of like each other. Now, to go further yet, let's take the derivative of both sides of this first equation. I didn't label this, but this is equation 1 up here. Take the derivative of both sides of that, the derivative with respect to x. So what will that yield? Well, what you get is the derivative with respect to x of, well, we already had the derivative with respect to x of e. So it's the second derivative with respect to x of e. And over on this side, you'd have the derivative with respect to x of the derivative with respect to time of bz. Okay. Well, let's switch the order of those two. You're allowed to do that. If you're going to take two derivatives, you can take them in either order. And so let's switch the order of those two, because if we do, then we get a quantity over here that we actually have in our second equation. And we can substitute. So let's substitute. And if we substitute from equation 2, then what you have here on the left, I just wrote it as the second derivative rather than two derivatives in a row. And on the right, I'm taking the negative time derivative of this thing, which is, according to the second equation, all of that stuff. Well, all of that stuff is mostly a bunch of constants, and those can be moved outside of the integral. And then what do you have? You've got a derivative of a derivative, both with respect to time. So that's just the second derivative with respect to time. And so that's what we have down here. So I've moved the constants outside. And notice, by the way, we pick up two minus signs. We picked up another one from here, We had one up there. Those two minus signs end up canceling, and we have a positive one. This is the amazing discovery. At this point, what we have is what is known as the wave equation. Whenever you get the second time derivative related to the second space derivative, you get waves. Let's see how. Let's try putting some waves in and see what happens. So imagine that that we think the answer might be an electric field that's traveling along the x direction. This would be our sort of generic form for an electric field that's varying and moving like a wave, a sinusoidal wave, with omega being the angular frequency and k being the, oh, what do we call that? We've been calling that the, I think some books call it the wave number. I don't like that because that's not the same as the wave number spectroscopists choose. We'll call it the K number, I guess. Anyhow, so the angular frequency and the K number are the two parameters in this wave. It's also got an amplitude, some E0 that it starts out at. So this is just kind of a generic wave, and what I want to do is plug this in to the equation that we just found. So we had this wave equation up here. I want to plug this into the wave equation. So let's see whether this is in fact a solution of that equation. Remember, this equation, it's a differential equation. It's not an equation that you can find, you know, what's E? What's the answer to this equation? It's not 5 or 62 volts per meter or something like that. It's a function. The answer to this equation is a function of some sort. And so here's a possible function that might be the answer to it. But we have a bunch of unknown parameters in here, E0, omega, and K. Now T and X are not parameters. Those are the variables that it's written in terms of. But these others are just sort of unknown parameters. And it could be that when we plug it in, we'll find, oh, you can't just have any value of those parameters. Let's find out. So the first thing we have to do is take derivatives so that we can plug them in. We're asked for the second time and the second space derivative of this thing. So let's take the derivatives one at a time. Here's the original function. Take one derivative with respect to x. Well, sine becomes cosine. E0 just comes down, that's a constant. But now we have to take the derivative. Sine becomes, yeah, cosine. And then we have to take the derivative of what's inside here with respect to x. And that's just going to be minus k. So that's what comes out. That's the derivative of what's inside there is minus k. Then we take another derivative with respect to x. So take the derivative of that expression. Cosine becomes minus sine. Which you'd think would make this positive, but when we take the derivative, out comes another factor of minus k, and that keeps it negative. So we end up with minus k squared E0 sine of omega t minus kx. So that's the expression we get. If you try taking the derivative with respect to time, it looks very similar, except what's coming out each time is not minus k, but omega. So we have an omega that comes out in front here, and another factor of omega that comes out in front here. The first time from sine to cosine, we didn't get a minus sign, but from cosine to sine, we do get a minus sign. Now plug these into the equation that we had up there, and you'll have the following result. So here is that expression substituted in as the second derivative of E. And then we take mu 0 epsilon naught and then substitute this other in for the second derivative of E. with respect to time this time. Well, a whole lot of stuff cancels. You look at this and you see, wow, sine omega t minus kx is on both sides of this equation. That can cancel out. So let's cancel it out and see what's left. There you have it. K squared is equal to mu 0 epsilon naught omega squared. Now, mu 0 and epsilon naught, those are universal constants. Those are physical constants. You know the value of those. But K and omega, those are the parameters of our wave. Those are the things that we were just sort of putting in there as any old value. Let's see what the limits are. Now we find out, well, you can't just have any value of K and omega. They have to be related by this particular formula. So we've got some constraints on K and omega. And interestingly, those constraints, in order to satisfy this relation, that fixes how fast the wave is traveling. If you remember the formula for the velocity of a wave, the formula for the velocity of a wave, one way of writing it is just omega divided by K. You could also write it as, what was it, distance divided by time. Lambda divided by the period would be another way to write it. But one way is omega divided by K. Well, it shouldn't be too hard to rearrange this equation to figure out what omega divided by K is. And if you work through that, figure out what is omega divided by K, and substitute that into this, you end up with the fact that the velocity of the wave is given by these constants, the square root of 1 over mu naught times epsilon naught. That's interesting. These constants were already known. When Maxwell was doing this work, electricity and magnetism had been studied, and most of these equations had been found. These constants were known. And so he goes through this whole development and discovers that waves should be possible in this area, in this phenomenon. And now he's just calculated that these waves will have a fixed speed. And the question is, what is the number? And so he calculated the speed, and it came out to this number right here. Here's the value of mu naught that you should be familiar with, 4 pi 10 to the minus 7. And here's epsilon naught. Do you remember that? 8.85 times 10 to the minus 12. I didn't put the units in here. But this comes out as 3 times 10 to the 8th meters per second. And that number was already known. That had already been discovered to be the speed of visible light. Visible light was not thought to be related to this phenomenon at all. But people had been investigating it for a long time, had measured the speed of visible light by mechanical means, some very clever mechanical means. And this suggests there must be some connection between these two, to look at this completely other phenomenon, electricity and magnetism, and go through and study and find out that you could have waves in this phenomenon. And it turns out that the waves in this phenomenon would have exactly the same speed as the already known speed of visible light. Well, Maxwell stated it this way: we can scarcely avoid the inference that light, visible light he meant, consists in the transverse undulation of the same medium, which is the cause of electric and magnetic phenomena. So in Maxwell in 1865, he was predicting the possibility of radio waves and also explaining that light must be this same kind of wave. He did this in 1865. He himself died in 1879, quite some time later. But it was even after that yet that finally Hertz in 1887 observed actual radio waves in the laboratory. This is an unusual case where theory was way ahead of experiment. In general, things are the other way around. but this is a remarkable piece of theoretical work by James Clerk Maxwell.